Hello everyone. In this video, we are going to use your studio to find Newmark deformation for slope. So I'm going to open a new analysis. I'm going to use metric units and the size letter. I'm going to define my project. So I'm going to name it Newmark Deformation for slope or seismic slope stability. I'm going to close this and add a geometry, two-dimensional. The first analysis that we're adding is going to be QUAKE W initial static analysis to calculate our initial stresses. Okay, so I'm also going to save this. We are going to sketch, and we are going to sketch our axes. Our elevation is going to be in meters. Our distance is going to be in meters. Based on the geometry that I have, I want the x-axis to be about 50 meters and y-axis to be 25 meters. And I want my increments to be 5. I'm going to zoom this to my window. I have my axes ready. So I'm going to define my points. And here are my points. I already have them written based on my geometry. I'm just going to enter them. 20 and 0. 45 and 0. 45, 10. 30 and 10. 20 and 20. 0 and 20. And 0 and 0. The slope that I have has a slope of 1, 1 or 45 degrees. The height of the slope is 10 meters. So I'm going to sketch some lines to show my geometry. So I'm going to go from here, 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 and here. So I have the geometry. Now I'm going to draw a region. I'm going to create 2 regions. One here and one here. The next step is to define our materials. I'm going to add a material. I'm going to name it soil. I'm going to use linear elastic, although it's not realistic, but for simplicity, we use linear elastic. I'm going to use 18 kilonewtons per cubic meter for unit weight, Poisson's ratio 0.334, damping ratio 0.1, and Gmax 20,000 kilopascal. And we assume dry condition for simplicity. Then I'm going to define or draw my materials, one here and one here. And I'm going to save this. The next step is to define our draw our finish properties. And I'm going to use 1 meter lengths for our mesh sizes. As you can see, here's the mesh. I have 762 nodes and 700 elements. So now we have to define our boundary conditions. If you go to draw boundary conditions, we already have fixed x, fixed xy, and fixed y defined. And those are the ones that we're going to use. So you don't need to define anything new. For boundary conditions, when you are drawing them, we are going to use fixed x and y for the bottom. And for the sides, because this is a static condition and we don't have any lateral load, we are going to close the movement from left to right, but we are allowing the soil to settle in a vertical direction. So our x's are closed for left and right boundary conditions. So I'm going to save this. I'm going to verify there's no warnings. I can stop running this. You don't need to run every time, but or after each analysis, but I'm just doing it to make sure everything is working the way we want it to. Okay. I don't want to see these notes, so I'm just going to close that. And we can draw some contours. For instance, if we want to see shear stresses. Also, I can add the legend. And these shows our shear stresses in the static condition before the earthquake happens or before we apply the load. If you want to see the slope stability of this slope in a static condition, we can add a slope stability analysis to our analysis tree. So I'm going to use the slope W analysis, and I'm going to use QUAKE W stress. So I am going to rename this to static slope stability, because this is for the static condition. And I'm going to go to the definition view, not results view. So here we have to do a few things. We have to define our materials, and I'm going to use the same material that we had, and I'm going to add a more chrome material model to it, and I'm going to give a phi of friction angle of 28 degrees and cohesion of 8 kilopascal. And I'm going to close this. And we need to define project. So here we are going to use our parent analysis, which is the initial static. We don't have any water, so I'm just going to put none. For slip surface, we are going to have a failure from left to right. I'm going to use entry and exit points, and I'm going to save 5 critical slip surfaces. The rest, you can leave it as it is. We are going to close this. And then I'm going to draw my slip surface, entry and exit. So I'm just going to do 12 and 20 and 18 and 20 for the left side. And for the right side, I'm assuming that all the failure surfaces are passing through the slope's toe. So I'm just going to put it 10 or 40, sorry, 30 and 10. So we have these and these. So we should be good to run the analysis and see what's our factor of safety for the static analysis. Okay, so we got 1.226, our factor of safety for the static condition. And this is the critical factor of safety or smallest factor of safety. And if you want to, you can just look at different slip surfaces and see the other values of factor of safety. And this is our critical one. Okay, so now I'm going back to the definition view. I'm going to add my dynamic analysis to my analysis tree. And they're going to be using the results of initial static analysis. So I'm going to add analysis to that, QUAKE W, and I'm going to use equivalent linear dynamic analysis. So now, for this analysis, I need to change my boundary conditions. So I'm going to go to draw boundary conditions. And now the bottom is fixed in both sides, but the left can be free to go to the left and right, but it doesn't move up and down because our earthquake is in the X direction. We don't have any vertical component for it. So I'm going to use fixed Y for left and right sides. If I want to use numerical or Newmark sliding block analysis, I'm going to add another analysis under this. But before I do that, let me double check my project definitions. I need to add the earthquake load to this. So we have our parent analysis, which is the initial static. For convergence, we're going to use max number of 10 iterations. For time, here it's where I'm going to enter my earthquake record. And we don't need to change those. So I'm going to copy and paste my earthquake records here. So I'm going to go here, define. Here, I'm going to paste. And I'm going to do base correction if I want to view my record. And I'm going to close this. And close this. Let me double check. See if we have it. We do have them here. So we're good to go. And now it's the time to add our Newmark analysis, which we go to the slope W, and then we go QUAKE W Newmark deformation. And we have it here. And now we can define our project. So we have Newmark deformation. We're going to use our parent analysis is going to be our QUAKE W. And slip surfaces, we are going to use the critical slip surfaces that we have from our other GeoStudio file, which is static slope stability. So I have to browse this and look at my analysis. And this is the one that I just created and found the critical factor of safety. So I'm going to select this one for the time. We're good. Advanced is good. And I'm going to close this. So I'm ready to run this analysis, and I should be able to get my deformations. This might take a while. The initial static analysis is done. The static slope stability is done. Now, the dynamic analysis is in process. And after that one, the Newmark deformation is going to be solved. And we will be able to see the results. Just to explain about Newmark deformation or Newmark analysis, what it does, it just say, okay, so if the factor of safety sometime during shaking goes below 1, that means you are going to have movements for your slope. And when the factor of safety is smaller than 1 or it's equal to 1, and then you can find acceleration at when the factor of safety is equal to 1. And that would be your yield acceleration. You can, if you integrate the acceleration graph at points that your acceleration is bigger than yield acceleration, you can find the velocity and maximum velocities. And then if you integrate that, you can find maximum deformations. And if you calculate the cumulative deformations, you can get the final maximum deformations due to that shaking. I'll show those on the graph so it makes more sense. So everything is done. If I want to see my graphs, I'll go here and I'm going to look at the factor of safety versus acceleration. As you can see, at some point, this factor of safety is going to be smaller than 1. The acceleration corresponding to that is going to be the yield acceleration. If you look at the acceleration graph versus time, if you draw a line at the point that average acceleration, yield acceleration happened, then whatever it's above it, which means it's bigger than the average, bigger than the yield acceleration, is going to cause the slope to move. And then if you get the integration of those, you will get the velocity distribution versus time. And if you get that integration of this one, then you'll be able to get your deformations. So for this particular slope and this particular earthquake record, your maximum deformations is going to be about 0.11. Thank you so much for your attention. Please let me know if you have any questions in the comments. Thank you.